I think most people are now in, and it's about 4 o'clock. So I will start this colloquium. I welcome everyone. My name is Daan, and I have the pleasure to introduce Stephan van der Zwaard to you today, who will give a presentation under the title Why Muscle Matters. This is the same title as the PhD thesis. He will present the work that he did in the PhD thesis and the work thereafter. This PhD thesis was awarded 3 times. He has received the prize from physiology, from sportgeneeskunde, and from human movement sciences. So I think we can expect an interesting presentation, and I give the floor to Stephan now.
Thank you very much, Hein, and thanks everyone for joining. So how do elite athletes achieve their exceptional performance, and how do they train to improve? In sports, we have typical sprinters on the one hand and typical endurance athletes on the other. But what if you need to combine both in your sports discipline? What muscle properties do you need to reach the finish line first? So first, for the ones who don't know me, a little bit of my background. So indeed, I did my PhD here at the Free University. Afterwards, I specialized also a little bit into data science. So I did a postmaster business analytics and data science. And I currently work as a researcher at the Leiden Institute of Advanced Computer Science. And also I'm a data scientist at Sport Data Valley, the national analytics platform for sports data. And last year I started as an assistant professor at the Free University too. And today I would like to focus mainly on my work during my PhD and the work after, as Hein already mentioned. So the roadmap for today consists of 3 topics. So first, I would like to tell you about the bottlenecks for combining high sprint and endurance performance. Then I would like to dive into the performance of elite athletes and their physiological profiles and what we can learn from that. And I would like to end with some training strategies and how these may be effective to combine a high sprint and endurance performance. So first, let's start with the bottlenecks. So in this picture, we see a clear example of a track cyclist, a track sprinter, Robert Fürstemann, German cyclist, Olympic cyclist, on the one hand, and on the other hand, we see Christopher Froome, a typical endurance athlete. If we look more closely to them, we can see that there's a remarkable difference in their thigh volume. So Robert Fürstemann actually has had his trousers made by separate people because all his thighs were just too big. So I think it's like 85 centimeters in circumference. So it's actually more than my waist. So you can imagine it's like it's, he has quite substantial quadriceps. On the other hand, Christopher Froome has much smaller, but of course he also needs to go up the mountains. And he needs to sustain for a long time. So that's a big difference. Also, if you look more closely, then we know that a large muscle size or large muscle volume is helpful to reach high peak power outputs. On the other hand, if you look at the endurance side, we know that a high oxidative capacity, so the capacity to utilize oxygen to make the energy to sustain a prolonged exercise, is important on that side. However, if you look at these 2 determinants at the muscle fiber level, then we see that there is actually an inverse relationship between these 2. So this means that they cannot be easily combined. That has been studied before already. So by one of my supervisors, Willem van der Laarse, he actually analyzed these 2 traits throughout the animal kingdom. So what we see here on the y-axis is the fiber VO2 max, or the oxidative capacity of the mitochondria. And on the x-axis, we have the fiber cross-sectional area, so the fiber size. And we go here from the shrew, mice, rats, rabbits, humans, and we have the toads and the xenopus there as well. So these are able to jump only once or a couple of times, and then they have to rest. All these they can sustain for a long time, but they don't have the power. So if you look at this inverse relationship, it seems quite profound. And the question now is, of course, if this is the case and it's so tightly regulated, can you actually circumvent this problem and maybe be able to combine a high oxidative capacity with large fiber size? Is this possible? Well, if anyone can, are elite athletes able to do so? That is the question. And might this also be a solution to combine a high sprint and endurance performance? I would like to walk you through all of this later in the talk as well. So if we look at performance and the physiological profiles, we did 2 separate studies, one in rowing and one in cycling. These were all elite athletes doing a lot of high-level work. So I'd like to walk you through that. So first, let's start with the study in rowers. And I don't know why. Yeah, there it goes. So the aim of this study was to identify the critical determinants of rowing ergometer, sprint, and endurance performance. And we looked at different levels, so at the whole body level, but also at the whole muscle level. And I'll tell you a little bit more about that later. So 18 subjects were included in this study, and they all competed at the Olympic level. So I think all of them went to the Rio Olympics. So yeah, quite a good level. And here you can see their characteristics. So actually, the rowing power output they produced was quite substantial. So almost 500 watts on the 2K for the males. And notice that it's both lightweight and heavyweight males and females that are included. So it's quite a various group with different boats that are included. But 18 in total, and of course there aren't as many Olympic rowers, so that's of course something you have to consider. Also, if you look at the height, it's going up to 2 meters, which is something you may recognize from the physique of these rowers that you may have seen in real life or on television. Yeah, so what did these rowers all do? So they did different things. So first of all, they did a 2,000 meter rowing ergometer time trial. So not in the water, because there you have, of course, the influence of wind and weather conditions, and we don't want this. So that's why we did the rowing ergometer time trial. And on the other end, we also analyzed their muscle morphology, and that morphology was measured using 3D ultrasound. And how did we do this? Well, this is a schematic of the setup, which Guido Weide has put a lot of effort in making this possible here at the Free University. So that's really nice that we could actually use this technology. So the rowers, here you only see the lower limb, but we're sitting on a bench in a fixed angle, a 90-degree knee angle. So the quadriceps, particularly the vastus lateralis, was scanned using the ultrasound probe, which you can see right here. And on top of the ultrasound probe, we have a cluster marker. And this cluster marker is tracked by the OptoTrack device that you can see right here. So this means that while you're scanning over the muscle and capturing all the ultrasound images, we at the same time are also measuring how this probe is positioned in space. And subsequently, we merge these two data sets to actually reconstruct a 3D volume and actually place all these images in the right angle in a 3D voxel array, which we can analyze afterwards. So actually, we need this cluster marker to combine the echo or the ultrasound device with the position of the ultrasound probe. And these are the images that are that you get from that. So this is actually a 3D reconstruction of the vastus lateralis muscle, which you can see right here. actually by manually segmenting all these anatomical cross sections. And here in the bottom, you can see here's the femur with the knee, with the insertion and origin here to trochanter major. And we can see that the vas lateralis is also here. This is the same, but then in a different plane. And we also looked at the mid-longitudinal vesicle plane, which is actually the plane where all the vesicles are clearly visible. And we actually measure the vesicle length and the vesicle angle in that plane, which are all important parameters, because if you have longer vesicles, you can shorten these quicker and get a lot of speed. So this helps for the power. But also if you have a lot of sarcomers in parallel, you all know this likely, then you can produce more force. So these are all things that we can actually extract from this ultrasound measurement. And here you see an example of 3 different participants or subjects. This is an 81-year-old cadaver. You also see that the quality is a little bit less. It's much more wide. So it's less clear. Also, the borders are less clear. Here we see a typical recreational male, and here we see an Olympic rower. So we can clearly see that there's a difference, at least in the muscle size in that sense. Of course, they can produce it for they can produce it a lot of power as a consequence of that. So now back to the comparison also between this performance measure and the muscle morphology. So what kind of variance is explained by, or how much of the differences in the performance is explained by this muscle morphology? And of course, their volume, as we noted from the beginning of the talk, may be an important parameter there. Here you see the relationship between the vas lateralis muscle volume and the rowing performance, the rowing ergometer performance in watts. So we have both the males and females. They were a bit separated, as you can see. If you would draw a line there, then the explained variance is 85%. I'll come back to it, because here you can see that there are 2 separate groups. If we go a little bit further, then there's much more overlap, but I'll show you in a little bit. But they didn't only do the rowing ergometer performance. They also did 2 separate tests, one for the sprint performance and one for the endurance performance. For the sprint performance, they did a Wingate test, which is a 30-second test that, well, maybe a lot of you also experienced. It's like 30 seconds dying, maybe. So getting all to the peak, and then trying to sustain as much as you can. We looked at the 1 second peak power from this test. And on the other hand, they did an incremental rowing test, maximal incremental rowing test, where we obtained the VO2 max from. So first, of course, it's interesting to see how these 2 performance measures explain the rowing ergometer performance, which is depicted right here. So the Wingate explained 81% differences, and the VO2 max 90%. However, if we combine the 2, so multiple linear regression showed that 98% of the differences were explained. So in that sense, the rowing is clearly a combination of this sprint and endurance. Now, if we go to the morphology and see how the VO2 max and the Wingate peak power are related to that, then we can see that for the VO2 max, the relationship is 0.66, the R squared. And for the Wingate, it's 0.82. But here you can clearly see that there are overlapping females and males, in the sense that we have or large females here and or shorter males. But they are all clearly in line in that sense. So here the muscle volume explains a lot of the differences in the Wingate peak power, similar to what we saw with the rowing ergometer performance. But we, of course, are also interested in the combination between these 2. So how are the VO2 and the Wingate measures related to each other? And we investigated this in the male rowers, showing a clear, distinct relationship, also negative, between the VO2 max on the y-axis and the Wingate peak power on the x-axis. And note that the variables were scaled using isometric scaling, so divided by lean body mass to the power of 2/3, just to get a measure relative to the same amount of body mass, lean body mass actually. So therefore we get rid of the comparison between the really large heavyweight males and the smaller lightweight males or females. But there's a relationship of minus 1.94, which is quite distinct. And now the question is, of course, can we figure out what explains the differences in this Wingate, or this normalized Wingate performance? And here we saw that, interestingly, the people with longer muscle fibers were the ones also achieving higher normalized Wingate power, with a relationship of 0.66. And we can ask the same for the y-axis. We have investigated this in a separate study already. This is a large study including cardiovascular patients, chronic heart failure patients, healthy subjects, and elite cyclists. And there we saw that the VO2 max was closely related to the oxidative capacity with a correlation of 0.94. So if we wrap up this first study, then we see that also in these elite rowers, it is challenging to combine a high sprint and endurance performance. Also, we saw that this rowing performance is strongly related to both the sprint and endurance performance measures. And this longer muscle fibers may be an important target for training if you want to combine high sprint and endurance performance. So that was what we saw in the rowers, but now let's focus on the cyclists. And here we performed a little bit more extensive profile, which I will walk you through. So the aim in these cyclists was to identify the critical determinants of combined sprint and endurance performance. And here we didn't look only at the whole body level, but also looked at parameters from the blood, the whole muscle, and also the muscle fiber. In this study, we included 28 subjects, and these were recruited from track sprinters, team pursuit, and road cyclists. And this group, they competed at the national, international, and the Olympic level. So also some of these went to Rio. And here you can see the subject characteristics. And the skin fold also indicates that these were indeed lean cyclists, which is something that may be recognizable. In these cyclists, we also took performance measures for the sprint and for their endurance performance. For the sprint, similar to the rowers, we did a Wingate test and took the 1 second peak power output. And for the endurance test, we did a time trial of 15 kilometers. And this 15 kilometers was just sufficient to let the sprinters sustain that, because of course we needed to make sure that they also were able to complete it. So it was a 15 kilometer time trial, and they took a little bit less than 20 minutes to do so. But also we did a whole physiological profile that we created from different physiological determinants. So for the oxygen uptake, we measured the performance VO2, which is the VO2 during this 15 kilometer time trial. We obtained VO2 max and VO2 at the lactate and ventilatory thresholds, and also the gross efficiency. In addition, we measured the oxygenation, the blood lactate after exercise. And we also did blood sampling, where we obtained hemoglobin, hematocrit, red blood cell count, mean corpuscular volume, and mean corpuscular hemoglobin concentrations. So all these measures were also included. And we also let them do an MVC, so maximal voluntary contraction, isometrically, a knee extension. And of course, we did the 3D ultrasound measures as well. And we could also combine these. So from the 3D ultrasound, we obtained the muscle volume, the vesicle length, physiological cross-sectional area, and pronation angle. We could also obtain specific force by combining this isometric force measurement with the PCSA. And also we obtained muscle biopsy samples from these elite cyclists, which was quite challenging, I must say. So we went with Richard Jaspers, we went through the whole Netherlands to convince these cyclists that they should really join our research, and luckily managed to obtain 28 cyclists who wanted to participate. Really, because who of the cyclists knows what is under there? Who knows what their fiber type is, or their oxidative capacity, or their myoglobin of the capillaries? Really getting insight into that, and also like what are your strong suits and what is things that you can maybe improve. That are the things that they were really convinced, okay, this is why I want to join your research. So we were lucky that they were included in that sense. And how does that work? So first they were anesthetized, the skin was anesthetized. Then they received a small insertion of the fascia, and then with a needle, the doctor obtained a little bit of muscle tissue, which we could analyze afterwards. And this is what it looks like. So this is the biopsy sample of an Olympic athlete. And what you can see, an Olympic track cyclist, what you can see is that on top, we have the different myosin heavy type stainings. So this is staining for type 1. You can see right here, so all the green muscle fibers are stained green. And 2A's is in this staining, and the 2X's is in this staining, but we can see that there are no 2X's at all in this cyclist. So it's mostly type 1 and a little bit of 2A's. You can see that this is exactly the same cells, but in a different section. On the bottom, we see on the left bottom here, the SDH staining, which is which can be used to predict this oxidative capacity. So the black things you can see right here, those are the mitochondria, or the mitochondrial activity, which is measured. And also here you can see that the type 1 fibers generally have higher SDH activity compared to the 2A's. And what you see here is the capillaries. So actually this cyclist has almost 9 capillaries around his fiber, which is quite impressive. And of course, this is helpful because all the oxygen needs to get into this muscle fiber to be able to make energy out of that. So that is, of course, helpful, but that is something that is quite unique to see, because recreational people, they only have like 3 or 4 capillaries around each fiber. And here we see the myoglobin staining with lower levels for the 2A compared to the 1. And the myoglobin, of course, transports the oxygen inside the muscle fiber. To compare this with actually a recreational person, we can see that here it's much more a 50-50 between type 1 fibers and between the type 2A fibers. And there's actually also some 2X, or actually hybrids between 2X and 2A that can be identified. Also, the staining for the SDH is a little bit lighter. We can see that there are definitely less capillaries, and also the myoglobin is shown there. But now let us get back to the results. So for the performance, we can actually look at the same thing as what we saw for the rower. So is it actually difficult to combine both a high sprint and endurance performance? And if we took the time trial performance on the y-axis and the Wingate performance on the x-axis, we can indeed see that in this cyclist, again normalized to lean body mass to the power of 2/3, that there's a clear negative relationship here as well. The R is minus 0.66. And the question now is, can we explain also again the differences in this Wingate performance, but also the differences in this endurance performance? And maybe even more interestingly, can we understand who of this group is able to combine a better sprint and endurance performance? So what properties do they have? What solutions did they find to actually get above this average line of the group? So these are the ones who are worse in combining sprint and endurance, and these are the ones who do it really well. And of course, we want to know, can we actually explain some variance there? So the whole profile and all the measurements I just described you, we can evaluate how much of the variance is explained by these. I understand that this is quite a full slide, so I'll walk you through it. So on the top panel here in blue, you can see the determinants, different determinants for the peak power of the wing gait. We can see that, for instance, muscle volume explains 38% of the differences in wing gait performance, and also the type 2 fibers here. So the ones with more type 2 fibers also have a higher peak power, which is something you would expect. But it's also like, how much of the variance can you explain? Using multiple regression, we can also see that the combination of muscle volume and fiber type explains 65% of the differences in this wing gait performance. Also, the combination of type 2 fibers and vesicle length, and this is excluding the, so this is a subgroup without the sprinters, almost explains half of it. So that is also important to note. If you look at the endurance performance or the time trial performance, then of course what you can expect is that performance VO2, VO2 max, VO2 at thresholds, they explain quite a large portion of the differences, and also efficiency. But if you look at the blood, we see some parameters there that can be of interest. So mostly the more advanced, or the mean corpuscular hemoglobin concentration, that explains almost 30% of the differences, but hematocrit didn't explain anything, or not significantly. Within the muscle, we have this the fiber types, the myoglobin, the capillaries. Those are the ones that explain a lot of the variance there. So that is also important to note. But now the question is for the combination of the two, and there aren't as much predictors. Of course, you also have noise, but there are some predictors that are there, and that is, these are tendencies. So we have a tendency for muscle volume, for vesicle length, but in the subgroup without the sprinters, vesicle length is significant, and performance VO2 and gross efficiency are also important. If you look at the multiple regression, then we can see that efficiency and volume and performance VO2 and vesicle length explain some portion of the differences. So if you would summarize all these results, then it may be highlighted that vesicle length, as well as this performance VO2, may be important to take a closer look at. This performance VO2 is of course a whole body measure, so can we also dive a little bit deeper into that? And that's what we did. So we saw that this performance VO2 is actually explained by the oxidative capacity, the capillaries and the myoglobin, and a lower physiological cross-sectional area. Maybe you recognize this from the beginning of my talk. There is a negative relationship here as well with the oxidative capacity, which was the y-axis of this relationship, and the physiological cross-sectional area, which is not the fiber cross-sectional area, but a level higher. So the whole body physiological cross-sectional area there. So now, of course, the question is, do we also see this on the fiber level? So here we again have this inverse relationship, and we zoom it a little bit in. And now the question is, can these elite athletes actually get above this curve? And it turns out that they do. So actually it is above. Still within the group, there is a negative relationship with a correlation of minus 0.5. And if we look at what explains the product of the X and Y axis, so how far you get above this curve, then we saw that the capillaries there explain 34% of the differences. So the ones getting higher also have higher capillaries around their fibers, which was also shown in the example of the track cyclist. So if we wrap it all up, then we saw that there are some important predictors for sprint, for endurance, and for the combination of the two. And we have these long fibers, but also here the capillaries and myoglobin, and the long vesicles and the capillaries. Those seem to be the targets that we may investigate a little bit more, and to dive a little bit more into that as well. So wrapping up this second study of the cyclist, we saw that also in the cyclist, combining a high sprint and endurance performance seems to be challenging. depicted by this negative relationship. We learned more about the determinants of combined sprint and endurance performance based on the whole physiological profile. And from this, we distilled also potential targets for training, which could be the long muscle fibers and also the capillaries and the myoglobin. We can also summarize these two groups and their negative relationship in one picture. So we have again the sprint performance in the Wingate, and the endurance performance now is the VO2, because we have a value from that both for the rowers and the cyclists. Here we can see that the rowers are actually higher on the curve than the cyclists are. But note that the rowers were Olympic level and the cyclists were of national and international level. And there are 3 cyclists here that are actually within the confidence interval of the rowers. One of these cyclists had a VO2 max of 80, which is the number that they say you need to win the Tour de France, for instance. And one of these went actually to the Olympics. So it may be reasonable to, it may be that this is actually a difference in performance level that we see here. Each of the participants also get, on top of like the generic results that we get from it, they also get their individual results. So stating what is your performance relative to the group, and also what are your strong suits, what are your weaknesses that you may work on more. So you can actually see from all these determinants, okay, what can I improve more compared to what is my starting point? For instance, we had one cyclist who said, well, I can do a lot of resistance training, but it just doesn't help me. And when we looked at his fiber cross-sectional area, we already saw that it was very large. It was already like 9,000 squared micrometers, which is on the top end. So of course, this makes sense that, well, you can do it, but you don't grow your muscle in fiber size. So recently, we actually summarized the literature also a little bit on that, but then mostly focused on the endurance performance part. So skeletal muscle determinants of that, particularly highlighting that. So you can also take a look at that if you want to. But because of time, I will focus on 2 other studies. So this was mostly looking at performance, differences in performance, and explaining them by differences in the physiological profile. And this highlights potential targets to address in training. And now I would like to go over potential training strategies and how these may be helpful to improve performance of these elite athletes. So of course, you can train both for sprint and for endurance. But if you look at the literature, then if you concurrently train for sprint and endurance, or strength and endurance, that may be difficult. This is known as the interference effect. And this interference effect may be more pronounced in certain conditions. So if I briefly summarize the literature for you here. So especially for lower body power, this interference seems to exist. Also, if you do endurance in running mode rather than cycling, because you have more eccentric contractions, this may hamper you more, in the sense that the interference is larger, and the interference says that the improvement in muscle strength or muscle power is not as much when you combine both sprint and endurance training compared to when you do only the strength training itself. So it's mostly the strength part that is hampered from concurrently doing it rather than the endurance part. It also depends on the frequency and the duration of this endurance training. Also, whether you do endurance training with glycogen depleted, how close the sessions of strength and endurance are together. So is it within 6 hours or less or more? And of course, how long you do the concurrent training. You can imagine that these elite athletes who train 12, 15 times a week, it's getting more difficult to actually get sufficient time between these sessions. So of course, also training status is important, and also the order in which you do. So if you do first strength training, then endurance, or the other way around, that also has an effect. There also has been pointed out that some things may be extra helpful. So maybe focus on sprint training. So sprint training may improve endurance without having this interference effect. And also plyometric or eccentric training could be an interesting target, which we'll look at also a little bit, and training for efficiency and economy. But first, I would like to focus on this sprint training and how this may be helpful. So if we get back to the results from the previous study, then we saw two training targets that may be important. One was the longer vesicles, and the other one was the better capillarization or the higher myoglobin levels. And if you look into the literature, then what we see is that using different training methods. So what you see right here is we have 4 different groups. This is a study by Vogt et al. And one group performed their exercises in normoxia, so just regular altitude, so sea level. And they had a high intensity training. And we also have a group that did the same high intensity training, but then also got simulated hypoxia. So this is simulated at almost 4,000 meters of altitude. And then we have the normoxic group that trained low and the hypoxic group that trained low. So we have 4 separate groups. And what you can see is both for the VEGF, which is a marker for capillarization, and for the myoglobin, we saw that only the hypoxic group with high intensity training, that is the one that increases this marker. So if you get back, so from the cycling study, we learned, okay, we may want to focus on myoglobin and capillarization. From literature here, and also different literature, we know that the high intensity is very important. And this can be because of the flow through the capillaries. This can also be because of the oxygen concentrations, the oxygen pressure within the muscle. But this points towards having high intensity exercise, but on top of that also performing it in less oxygen environments. So that is actually what we did. We collaborated with a group in Switzerland and in France and in Belgium. And this study was actually executed in Qatar. And they looked at muscle adaptations in elite athletes after repeated sprint training and altitude training. So actually, we looked at this sprint training and then looked at the muscle characteristics. So similar to the slide I showed you way in the back, we can see that in team sport also it's difficult not only to have this maximal sprint, because of course you need to sprint a lot of times, but also you need to recover quickly. Because, well, you notice from soccer that winning games are sometimes won in the last minutes because one team can sustain it longer and recover more quickly. So this is, of course, definitely important in team sports. So what we saw in this study, so this group already published the results for the performance, but they didn't look yet at the muscle characteristics. And that's what I'm going to show you right now. So what they already saw is that this repeated sprint ability is enhanced after combining a live high, train low altitude training camp with repeated sprint training. And they did this only for 2 weeks. So that's quite short. And they did this in elite team sport players, hockey players, and they also took the muscle biopsy samples. So here you see how they improved. So they did repeated sprints, and the time they used to complete those sprints, that's what you can see right here. So that is the baseline, and if it's gets less, then it's better, of course. So we see that in 2 of the groups, that did the repeated sprints, there it was improved. In the white group, it didn't improve. That was the control group. So again, also in this context, we want maximal sprints and we want fast recovery, and we have the same picture there. So larger muscle size may help to sprint better. A higher oxidative capacity may help to recover quicker, but we still have this inverse relationship that we need to, deal with. But the cyclists were able to get above this, and the question now is, of course, also like these elite hockey players, are they also on the same line, or can they get even more above it? How does this training affect it? So I will definitely tell you a little bit about that. So the aim of this study was to look at the muscle adaptations in response to this repeated sprint training at altitude or with the training camp, and look specifically at the differences in the muscle oxidative capacity, muscle fiber size, and the oxygen supply capacity. We included 18 subjects. These were all competing at the international level from Belgium, Dutch, and Spanish first division clubs. And here you can see their characteristics. And here you can see the whole protocol, what they did. Here you can see what they did. So we have the repeated sprint training here on top. The blue group, they did the repeated sprints on sea level, and the red group did the repeated sprints at 3,000 meters of altitude. And then the altitude training consists of living high and training low. So all the groups trained low, which you can see right here. But only the red and the blue groups went to altitude during this 2-week intervention. And before and after this intervention, a muscle biopsy sample was taken, and also 3 weeks later on to see how the adaptations persisted. Again, this is a similar picture as what you saw before. So here we see the staining for type 1, type 2A, and 2X, and also SDH, capillarization, and myoglobin. And I really would like to point out this result in the sense that we have the control group, we have the group that sprinted low but had an altitude camp at 3,000 meters, and we had the group that sprinted also at high intensity, but also the hypoxia. So we would expect most of this red group. And here we look at the SDH activity, which is the y-axis of this curve we saw before. And interestingly, both in the type 1 fibers and the type 2 fibers, this group shows the most profound increase in the oxidative capacity, which is 32% and 37%. And you have to remember that these are elite hockey players. So even these elite hockey players within 2 weeks are able to increase their oxidative capacity by so much. The downside of this is after the 3 weeks of doing nothing, then they lose quite a bit of this again. So 3 weeks later, only 12% of this improvement is left. And if we now go to the curve that I showed you before, so here we have the standard curve from all the animals. Here we have the curve from the cyclists. Then this is where all the elite hockey players started. This is at the start of the training intervention. So similar to the, you may say that they start at the same region as the cyclists did. And also here, the differences above this curve, the differences in this combination was explained by both myoglobin and capillaries. So also here, the oxygen supply is very important to explain how the ones who are better in combining this VO2 max and fiber cross-sectional area. And then after the training, we saw that the group, the live high, train low, and high group, so the red group is actually the one who improved very much in this oxidative capacity, but not so much in the fiber size. And this other group doing the repeated sprints low, they had a little bit of improvement in both. On average is 30%. And this is also explained by improvements in the capillaries. So if we summarize this, then we know that it is possible to improve both fiber VO2 max and fiber cross-sectional area. Something we wouldn't have thought maybe from the clearly inverse relationship, and that the myoglobin and capillaries may be important there and can be improved by the repeated sprint training. So this is what this is actually what I just mentioned. I see that the time is, I hope you don't have too much noise here in the background. I'm sorry for that. I'll move on. So I have one final training study which I would like to address with you. And this goes towards the fiber length and lengthening of the fiber. So this particularly focus on this eccentric and plyometric training that may be helpful in the context of combining a high sprint and endurance performance in athletes. So what do we know from literature? Well, there is much literature out there, but also plyometric training. If we focus on that, then we know that plyometric training can improve the vesicle length or the muscle fiber level already within 2 weeks. So this is a group of 8 healthy males. It's by a study of Monty in 2020. And we saw that already in 2 weeks, they have a significant improvement in vesicle length by doing this plyometric training. What is this plyometric training? It's fast contractions. It's like speed skating jumps, squat jumps, jumping with aqua bags. It's a lot of different things that you can do, but it's high velocity exercises. So that is what we will focus on in the next study. And the aim here, so this is just recently published, or it's only accepted, but the publication will be out probably in a couple of weeks. You can already find it. But the aim here was to investigate how morphology changes and how the functional adaptations occur in elite rowers, elite female rowers, during the general and competitive preparation phase of their rowing season. Here we had 21 female rowers, 19 participated in World Championship and 11 in Olympic Games. So also quite elite level. And they did 8 weeks of concurrent training with high load resistance. And they did a subsequent group of 7 did a 16 weeks of concurrent training with additional plyometric loading. So this is the plyometric aspect being included as well. And we did testing at baseline, after the general preparation, and after the plyometric, the competitive preparation. So looking at the results, how did they improve? Well, during the general preparation, they significantly improved their rowing ergometer performance, which is of course the most important measure for these rowers. And what changed in the muscle morphology? So we saw that the volume didn't change as much, no change at all. Also the PCSA, so the fiber cross-sectional area, didn't change. But interestingly, we saw a decrease in the vesicle length. So by doing this strength training that is, or resistance training that is focused on high loads, you can imagine that you're doing like the shorter contractions and mostly focus on producing a lot of force, but then the vesicle length is actually reduced. If you go to the competitive preparation, and you have to know that this is a smaller sample, then we can see that they actually made a larger improvement there even. So quite a big improvements. It's about 5% higher, 5-6% higher. And then volume, not significant. Also PCSA is similar, but also non-significant. And for the vesicle length, we see that there is a step, but it's not significant because only 7 rowers were included. And that's also what you can see in the right bottom here. So on average, the effect size was almost 1, but because the variation is so high, it didn't reach significance because it still goes through the 0. But we see a similar tendency, right? So also in this group, although not all of them, but actually some of them definitely improved their vesicle length. So these are the individual adaptations. On the right-hand side, after competitive preparation, so this is the slide you saw before, and you see that there are actually some people, elite rowers, who improved their vesicle length with over 30%. While with the same stimulus, there were others who were actually not improving as much, or even reducing their vesicle length. This is very important. So giving the same stimulus, in general, you would say, okay, well, this plyometric training may induce longer vesicles. Well, we saw indeed an effect size with 30% improvements and almost an effect size of 1. So it's going that direction, but within the group, there are large individual differences. And this, of course, is important to focus on next. So can we explain who responds differently to the same training stimulus? And is it also explained by where you start with? And for this group, we actually saw that some of the differences in the performance measure were actually explained by also the differences in morphology. Looking at the time, I will speed up a little bit. I'm almost done here. So the conclusion here is that the rowers improved their ergometric performance both following the general and competitive preparation. Training adaptations were larger than expected. So for the vesicle length, we saw change up to 30%, but also for the cross-sectional area, we saw large improvements. And this was mainly at the other, so the general preparation. And there were large individual differences who deserve much more attention also in the future. I think data science there is, of course, also a very important tool to use. So to conclude, I've walked you through all these different aspects, showed the bottlenecks of combining high sprint endurance performance, looked at performance and physiological profiles, and also at training strategies that may be helpful. So what have we learned? Can we tell a little bit better if you are a sprint or an endurance athlete? So based on this wingate performance and the endurance performance, do you know where you start and also where you want to go? Can we use this also for talent identification? Compare talents where they are compared to where these athletes, for instance, are. We can learn from the physiological profile, not only by general training targets, but also for the individual. What are your specific things to focus on? And also, of course, the individual training optimization, and learn more about that. Of course, there are a lot of people who put a lot of effort in this research to make this happen. So I would like to thank all the organizations and collaborators for this research. So thanks, and let me know if you have any questions. Put on the light, by the way.
Thank you, Stephan, for this nice presentation. It's open for questions right now. Are there any questions? Can I start with a question while the rest is still thinking? I have a question, Stephan, regarding the effect of age on the profile of that you're discussing. So I have the impression that the oxidative capacity stays better with age, but that the sprint capacity decreases faster. Is that true? And is there any research that monitors the effect of age on the combined profile?
I'm not aware of there being a study looking exactly at the effect of age on this whole profile, but of course, aging, sarcopenia, of course, then you lose a little bit of muscle. So also there with the muscle power, the wingate is of course also lower in older people, and also the oxidative capacity. That's also what we saw in the heart patients, and we know that with every decade this reduces. Also partly by the sarcopenia, but also just because the mitochondria well, you have fewer mitochondria. But I don't know any study that looked at that exact effects. I'm really interested to take a look at that as well. So maybe future studies will include that.
Okay, thank you, Stephan. And other questions?
I have one, if I may. Yeah, Stephan, thank you for this presentation. Could you comment on the individual findings that you saw in the last study? The increase in fiber length of 30%.
Yeah,
it's quite impressive. How do I see that in the morphology of the muscle? Because where can you gain 30%? I don't assume that they were full-grown athletes, so they haven't any change in the femur lengths or something like that.
No, usually you see a combination. So it's not only the fiber length that increases, but it's also the pronation angle that decreases concurrently with that. So yeah, usually the sarcomeres are built at the end, so to say. And this 30%, yeah, it's like 2 centimeters, something like that. So it's quite substantial, but it's growth that we've seen also in other literature as well. So this can definitely happen. Also, Blažević in 2005, they found also such large improvements in that sense.
Because but I assume there's not much to gain from the changes in pronation angle. That in terms of, can you say how much of this 2 centimeters is due to the changes in pronation angle in your study, or is that am I asking for too much?
Well, I'm not sure if you can. Well, the pronation angle, of course, changes during an exercise, but of course, the vesicle length must. So in the same angle, so in the 60-degree angle that we measure in, we all standardize that. You of course need this longer fiber if you want to reduce this vesicle angle. If you know what I'm saying.
Yeah.
So I'm not sure. Well, so I'm not sure if you can say it is because the angle changes so much then that the vesicle length has to increase so much. But some. So
no, but the difference by how much? Yeah. So how? Yeah. Because I still have. I find it difficult to see that you can, because there must be an end to the fiber length increase that you can achieve.
Yeah, we have run a simulation model with Maarten Bobert on this to see and there is of course an optimum in how much you can improve or lengthen your vesicles at some point. So at some point you're just too long in a sense, so that your optimum isn't at the optimal angle where you do your exercises in.
Okay, thanks.
Okay, thank you. Can you unshare your screen, Stephan, so
sure, yeah.
You can have a better view on the people asking questions. There's room for other questions.
I have a question, Hein.
Oh.
Thanks, Stephan, for your very nice presentation. I had to write it down because I didn't know what some abbreviations meant in the starting of your presentation about the endurance performance. This MCV and MCH and MCHC. Yeah. All abbreviations with M, H, and C's. And V's. What is it, and what is the physiological explanation why you think that explains some of the variance in your endurance performance?
I've spoken them out. I think so. It is mean corpuscular volume. That's the MCV. It's all measures of the blood, so blood transport, and mean corpuscular hemoglobin and mean corpuscular hemoglobin concentrations. So these are all measures of the red blood cell compared to the volume they're in. So it's kind of a relative measure of the blood carrying capacity. So the oxygen carrying capacity in the blood.
And why would that correlate about 50% or explain almost 50% of your endurance capacity?
30. Yeah, that's a good question. Of course, we need to dive more into that. But within the group of cyclists, which were both sprint, team pursuit, and road cyclists, these differences are remarkable. And it's something that I wouldn't, I cannot pinpoint it right away in that sense.
But okay, let me ask it differently. Why did you pick those ones then before you started the study with let's measure these because they may be important?
Yeah, so what we decided is to do a complete blood count to get a broad overview of how this oxygen carrying capacity is in the blood, and these are standard measures that are done inside of that. So yeah, it's not that we pick them by hand, only we want to look at that. No.
Okay, thanks.
Thank you. It is 5 o'clock, and since Stephan is one of us and can be easily approached for other questions, I suggest to end this colloquium. And I want to thank Stephan again. Small applause for his nice presentation. And I hope to see you next time. I wish you a very nice day.